Welcome to Walkabout the Galaxy, the charmsy-turvy astronomy podcast where the science is universal, the opinions are personal, and the equipment is questionable. We are strange charm, top and down the astroquarks, also known as Josh Caldwell.
Addie Dove.
Jim Cooney.
And Audrey Martin.
It's scaring me there, Jim. Coming to you from
I'm here.
Coming to you from the Walkabout studio at the University of Central Florida with 3 real quarks and 1 virtual quark through a tenuous space-time subspace link. Be sure to follow us on Instagram and anywhere else we may happen to show up, but mainly Instagram where the facts aren't checked, but you can always trust the astroquarks. Check out our videos on YouTube. We are at Walkabout the Galaxy. You can email us at wtg@ucf.edu. Our stumper today is returnal. Sample returnal.
Okay.
Ooh, okay.
Sample returnal.
When you said returnal, Audrey was like, but then when you said sample returnal, she got
She
excited.
was like into that. Yeah. Tell me more about it.
Tell me.
A genie grants
me
you a
more.
wish.
Love it. Love
one
it.
single wish.
It's fine.
The only thing you can ask for is 1 kilogram of something from anywhere in the universe.
Oh.
So you can get a one kilogram of something from anywhere in the universe.
You gotta be careful how you answer this because, like, it's a mass thing, not a volume thing.
That's right.
Yeah.
So you could get like a kilogram of solar wind
Yeah, that's so much stuff.
if you wanted, but you'd have to like say, from 1 AU or whatever in our solar system or something like that. You can't say, I'll have my 1 kilogram composed of 1,000 separate grams taken from 1,000 different
Sure.
locations. Okay. So,
Okay.
any thoughts, any desires? Sample return. Audrey, you should have all sorts of really boring rock ideas coursing through your head right now.
So many
They might
boring
have
rocks.
icy. They might be icy rocks.
Burn.
Yeah. Oh man, yeah, this is a stumper.
What's yours, Jim? What's yours?
I'm oscillating between 2, but I think I would go with 1 kilogram of water from Europa's ocean.
Wow!
Really?
Look at you being all
to see
planetary.
what's living in there. Yeah.
That's a surprise. I was not expecting that.
The other thing was going to be I was going to get a kilogram. I'd be very interested in a kilogram of like core material from a neutron star.
Oh.
That's what I was thinking you were going to go.
Because we really have no idea like what the state of matter in there is, but it's so small an amount that it would be very hard to study that. So I want to see the creepy things.
It'd be a kilogram.
It'd be more than you wouldn't have it.
Yeah, a kilogram. But do you know how small that would be?
It would be so small.
Well, once you got it here, presumably it would
take it apart.
expand somehow.
Well, but
right?
I'm gonna. I have to have it in its
Pristine
nascent
condition.
form
In
there.
its
Yeah, the
yeah.
box.
compressed state.
We have a really good sample return capsule.
Yeah,
Okay.
yeah.
All right. So
Yeah.
you assume the sample return capsule keeps that core
In its
because
pristine state.
your point is that the core of the neutron star has got a star's worth of stuff crushing it.
Right. It's
On
the
top
pressures
of it.
in there are insane, and you have to keep that pressure in order to keep it in the
Because
same.
you want to know like about its actual physical state, not just like
What-
compositional.
Right. I know it's
stuff.
made of neutrons, but I want to know. It's neutrons under insane circumstances, so I want to see what it's like in there. Yeah.
How smushy they get.
Yeah.
Yeah, that's an interesting point because I was thinking like, oh, you could take a look at the inside of Jupiter or Saturn, like where this sort of metallic hydrogen region or something like
That'd be
that.
cool.
See what
That'd be cool.
See what that looks like. Yeah. Well, you definitely caught us by surprise with your astrobiology planetary answer there.
Answer. What about you, Audrey? Did you narrow it down?
Yeah, my first thought was obviously one of the Trojans.
Sure.
Trojan asteroids.
Bored.
Really?
Yeah,
I know.
That's what she studies.
I know,
We're
but
all so
She's so
surprised.
basic.
That's what I said. My first thought.
Yeah.
But
Okay.
my final thought
Oh.
is
Ever.
go to one of the hollows on Mercury
Ooh.
and get some of the hollow material because we don't know what it is or where it came from or how old it is or anything about it.
Hollows on
Yeah,
Mercury.
they're like-
did we talk
We
about?
have talked about
Yeah, they're
them,
like
yeah.
these not radar. They're high albedo patches that look kind of like scabs, usually in craters, but not necessarily in craters, and they're really small.
Small bright patches on Mercury.
Yeah,
Mercury's white heads.
basically.
that you wanna
Yeah.
look. Yeah. Okay.
Yeah, but we don't really know what it is.
Send Dr. Pimple Popper. She'll help you extract some material. Gross. I am trying to decide what sort of like diffuse nebular environment I want to sample. Because you could get so much material
Yeah.
for a kilogram. But I did like your solar wind idea too.
Yeah. I've got for myself, I have my basic answer. I'm trying desperately to think
Is
of
it
something more
Saturn's
interesting.
rings?
It is something
Yeah.
like that.
Yeah. What's your more exciting version?
That's what I'm saying.
Protoplanetary disk.
I'm struggling to come up with something
that's
more
fun.
Yeah, mine is
interesting.
I'm thinking like one of the like ALMA protoplanetary disks that we have these cool images of, and they've got these really diffuse, but also some dust. And like, what are the dust grain sizes? Like, we could sample a protoplanetary disk.
Oh yeah.
And we'll be talking about some of those protoplanetary disk images a little
Maybe
bit
that's
later.
why I thought of it.
Yeah, my basic one would be like
Josh.
1 kilogram. That a particle in Saturn's rings that weighs 1 kilogram. We do not know. Although maybe I think I would take a core sample, 1 kilogram, from the outer part of a big planetary ring particle. It's not the whole. Some of them are like going to weigh 100 or have mass of hundreds of
so you
kilograms.
want like a big thing, not just like a bunch of little
thing,
things.
a piece of one big particle, because some of these things we suspect may be super, super fluffy, like very, very low density.
So you also want your box to be able to keep the samples
Cold, fluffy, and everything like that. Yeah,
cold, fluffy
yeah.
sample.
So important distinction there. Okay, well,
Wow, that was fun.
So stumped.
maybe we'll get some of those things someday.
Yeah.
Okay.
It's possible.
Maybe in our lifetimes.
Yeah. Today we'll talk about the early days of stars, Io, exocomets,
Yes.
much more. But first, this episode of Walkabout the Galaxy is brought to you by the Lunar Highlands.
Yep.
For lush greenery, long winter nights, lots of rain, and abundant haggis, try the Scottish Highlands.
Oh, okay.
But if you'd like to get back to basics, consider a trip to the Lunar Highlands. You won't find sheep on this dramatic landscape, but you will find some of the oldest rocks and craters in the solar system. Enjoy a spin across this magnificent desolation in a lunar rover. Build a lunar sandman from the fine lunar dust. Take a load off and enjoy 1/6 gravity, and take in the spectacular views of the Earth, motionless in your sky day and night. Find your cosmic roots with a trip to the Lunar Highlands. A different holiday every day.
Different holiday.
Holiday Inn,
Oh,
It's reasonable.
but wrong.
Yeah. I kind of like it better than the right answer, actually.
Oh.
I kind of think Holiday Inn should go for that.
Oh.
Yeah.
I think that'd be a really
Well,
good
it's already
Holiday Inn.
taken.
Well,
It's got to be
I
the
think
holodeck company.
The
Hallmark.
the
Holodeck Company.
Holodeck Company.
Hallmark.
That's actually also better than the right answer.
Oh, I like Hallmark.
Hallmark.
It's not Hallmark,
Holodeck.
but I like that. Sandals Resort.
No, Scotland.
Oh. I almost said that, but I was like, no.
No, that would be too
That would be
stupid.
silly.
Josh would never do something that stupid.
That would be so basic.
Right.
This is
It's
the
kind of a
basic
basic
Josh
episode.
episode.
That's right. Yeah. Okay. So last time we had an abundance of space news because all the big rockets taking off and having interesting combinations of successes and failures. One of the things we talked about was a couple of lunar robots were launched successfully.
Yeah.
And they're taking, seems to be kind of common these days, a rather roundabout way to the moon for a robotic mission to the moon.
Yeah. I mean, most of these missions don't have a lot. So it was launched, they were both launched on the same Falcon 9 rocket and put into an Earth orbit. And so then like they have all of these missions have to have some propulsion on board to like navigate them. But a lot of them don't have a lot of propulsion though. So they have to take sort of circuitous routes to get to the moon. So the Firefly mission is taking like a 25 days. They're in Earth orbit and they've done 2 burns so far and nothing's gone splody. So that's super exciting.
good.
That's great.
And they are still in an Earth orbit, and then they're going to do a translunar injection burn in a week or 2 or something. Then they got to get into moon orbit. So yeah, they take these like
Take
much
their
more
time.
circuitous
Well,
routes that
there's
are more
nobody-
energetically favorable, and there's not people on board.
There's nobody on board to
So
starve to death or anything.
yeah,
so
or food to go bad.
Great.
or
Yeah.
anything, So
right.
That's always a plus.
The food isn't going to go bad.
yeah.
Right. Yeah. So everything is looking good for those missions. That's cool.
Yeah,
I saw
iSpace
that.
is the second one, and they also have been putting out a few updates that things are going well.
Things are going.
So.
Speaking of things going, we're recording this on January 24th, 2025. And earlier today, SpaceX launched its 11th Falcon 9 mission of the year.
Oh, really?
Yes. So in the first 24 days of the year, they have launched 11 Falcon 9s. and also, of course, Integrated Flight Test 7 of the Super Heavy
Yeah.
launch vehicle. The Starlinks, they used to be cranking out like 40 or 60 of those Starlinks per launch.
Okay.
Now it's like 23 or something
Oh,
because
it's
they're
smaller.
bigger.
Good.
Yeah.
Oh.
The satellites are bigger and whatever.
Hmm.
So crazy numbers of satellites going up.
That's so
There.
many.
And
That's so many.
And, you know, the number is increasing, but part of they have to like
They have to keep
Keep
launching
this
them
going
because they're in
forever.
such a low Earth orbit that they just keep coming back in.
right.
Oh, really?
Yeah. Yeah. Their
to do-
lifetime is short.
It's years. Yeah.
Years?
Yeah,
Single digit
Single digit
years.
I did not know that.
Yeah.
Yeah.
So they're in such a low Earth orbit that, like, I mean, that was why they had such a big problem because they did one launch and it was during like a solar storm and the atmosphere was all puffed up and
Yeah.
like I
They
don't know,
just
less than half
instantly-
of those went
yeah.
into the correct orbit, and they
The
all
rest of
got
them just burned up.
just burned up.
Oh my
Yeah.
God.
Not like instantly, but you know, they
Well,
didn't make
but,
it into
yeah.
data
Yeah,
taking
yeah.
orbit. Like, there's got to be so much interesting data about drag and all this stuff that like
that they're collecting
they're
from having all
collecting.
these. Yeah, all
So
those Starlink satellites are accidentally upper atmosphere in situ sensors.
I wonder if there's going to be any sort of like long-term cloud seeding because of all the material they're putting into the atmosphere. Maybe we're doing
Maybe.
a
Right.
what's it called? Terraforming,
Geoengineering.
geoengineering experiment without even think. There was that paper we
Ooh.
talked about that talked a little bit about that.
I actually am curious to know because with literally thousands of satellites
Yeah.
in, 350, 380 kilometers up,
Yeah.
those, the just tracking the orbits of those objects is providing some probably very interesting data
Yeah.
about how the upper atmosphere expands and
Breathing,
contracts
Oh,
day-to-day,
and responds
Right.
to changes in solar activity. And I imagine that data, I wonder if that data is publicly accessible through like space,
I mean,
Would
there's
it
like,
be?
there's like,
or
there's
if
like
it's
the tracking
proprietary to SpaceX.
data. Tracking data is available, so like whatever cadence you have for that, but
Yeah.
probably not as high a fidelity as like SpaceX data that they have like on board.
If you had the orbits, you could back out, how things are changing.
Yeah.
So, yeah. Anyway, that's interesting.
Yeah.
Yeah. Let's see. Our first topic, I'm looking at Audrey.
I'm looking back.
Yeah.
Wow, that's so nice.
Addie is in between. Jim's on the computer. That's the setting here at Walkabout Studios.
And now,
And now Audrey's going to talk to us about
Io.
Io.
Yay, Io. It's the most volcanically active
thing.
object in the solar system. It's got so many volcanoes that
How many
people-
volcanoes does it have?
Oh, I should have friggin' looked that up.
And
You're too young to know that the correct response to that is it's got so many volcanoes that that's a classic joke setup.
I know the classic joke setup.
Okay, I thought
I'm
maybe
not. That's
I'm
not.
familiar with the jokes.
I know
thought
what a
maybe,
joke is.
I thought maybe that was like only a 20th century thing. I thought maybe I'm the only one old enough to know that. I associate
Wow.
that with Johnny Carson. Tonight Show.
Oh, who's that?
How
Just
big
kidding.
was it? It's so
It was
big.
so big.
There's so many.
There's so many volcanoes that they thought it had a global magma ocean.
That's exactly what I was gonna say.
But
That's so
Do
funny.
you,
Wow.
think, do you think that it has more or fewer volcanoes than Earth?
Ooh,
that's a
more
good-
or fewer volcanoes than
Per
Earth?
square kilometer, I'm sure it has more.
Yeah,
but
per square kilometer.
It's small.
I think
That's true.
from
Probably
do,
fewer.
do you
It's
mean
gotta be-
active or
Oh,
what? You talking?
I don't know.
Oh,
probably not.
I thought,
Probably just
active
that are
is
there.
probably fewer.
and then you have to sort of define
Total there
what you mean by
a
active.
volcano.
Well, and also you have to
Like-
know
Do you
this
count seamounts?
and like spatial resolution. Like we have a lot of little volcanoes on Earth that we
Do
can
we?
count. Oh
Yeah.
yeah,
Like
tons.
you're counting Old Faithful as a little volcano.
No, but like
What
cinder cone
Yeah.
is a volcano they're very little.
Extinct.
They're made just cinders and like splatter cones.
What you're
Splat.
it sounds like you're talking about like
Geology?
your nephew's science fair project or something.
No, Sunset Crater right outside of Flagstaff. That's a cinder cone.
Sounds like it's a crater.
Is it an active volcano?
It's not currently active. No.
It actually sounds to me like something I'd get at Home Depot to like work on a
cinder
fence or
cone?
something. Cinder cone. Yeah.
That's like if you get pumice, they probably came from a cinder cone volcano. Yeah, because it's like very. There's a lot of like gases in the magma, and so it comes out and it's got a lot
Hummusy.
of
Okay.
got a lot of bubbles in it.
Jim, you
Is it-
stumped us.
Is it?
Sorry.
What's
Go
the-
ahead. Tell
what's-
me about
what's the answer?
No, but I
doing
want to
with
know
IO.
now. How many are there more on Earth or more on Io?
Well, one thing we know is, because you just said it yourself, Audrey, Io is the most volcanically active object in the solar system.
That's what I said.
So it has more active volcanoes than the Earth,
Okay,
period.
great.
Roughly 400 active volcanoes
On Io,
On
on
Io,
Io.
400.
Yes.
That's
Yeah.
a lot.
It is a lot.
Io's about the size of Earth's moon,
right.
and so and those volcanoes are huge too. Like they're
Over
not little volcanoes.
130 of which are erupting at any given time.
Oh my
Oh my
god.
gosh.
Wow, that's crazy.
That's crazy.
So it's not that
Yeah, don't
hard
go there, Popper.
to like leap to the conclusion like, oh, there's definitely like this magma ocean beneath the crust.
Only around 50 volcanoes erupt on Earth each year. This is just according to our space right now. So
Yeah, but I think
okay.
seems
Yeah.
accurate.
Yeah. Okay. Well,
So
surface area-wise, just roughly speaking, the Earth is
I think we're moving on.
got about 20 times the surface area of Io, I think.
Yeah.
oh, okay. That would make sense.
So a lot fewer per surface area then. Mm-hmm. Okay. What's fascinating and new about this?
Yeah, so there's the Juno spacecraft that's orbiting Jupiter, and because of that, we're able to get really good pictures of some of the satellites like Io. And when they went past Io the first time, they saw for the first time the poles of Io had a lot of volcanoes on them as well. We assumed, but we didn't know for sure.
Had not gotten a good look at them previously.
Right. And so that at first was confirmation. There's this like subsurface magma ocean beneath the crust that's feeding all of these volcanoes that are speckled
So-
pretty much evenly across
So-
the surface.
Right. So sort of like Europa has a global subsurface liquid water.
Right.
Probably.
We're speculating, does Io have a subsurface liquid rock
Right. Exactly.
mantle?
Yeah.
Yeah.
So the next step is it deforming like it should if it was one continuous magma ocean beneath the crust?
A global ocean of
Yeah,
molten.
it should be like, kind of more elastic and like putty. It should be like,
the surface
bending
of Io would be more flexy.
yeah. And they, using the data from Juno and previous data, historical data from another spacecraft, it's not. It's way more rigid than
Okay.
it would be. And using their models, they're able to say, no, there's actually no way there could be a magma ocean beneath the crust. So it has to be isolated pockets.
Local hot spots.
Yeah.
Interesting.
Yeah.
Okay.
Which for me, it just seems like that,
seems surprising.
yeah, like how would you get a whole bunch of individual hotspots?
Right.
As opposed
Because
to,
the
because
heat-
the energy is coming from like the tidal deformation.
which is global.
Right.
Which is, yeah.
Yeah.
Right.
So
the
more
the energy
questions.
is going in by deforming the whole thing,
Mm-hmm.
which is, why Europa has a global liquid water ocean, why Enceladus has a liquid water ocean. So, yeah, if you're
It's-
dumping energy sort of globally, it's not like, chunk of something radioactive here or there, something that's melting a local spot. So, interesting. I also think it's worth reminding everyone that we only have those pictures sort of because of a late last minute, okay, we'll put a camera on Juno, because it originally
right.
did not have a camera.
What?
Yeah, it's not part of the science mission of Juno.
Yeah. But that's
To
not what
take
this data. This
pictures.
data isn't picture data.
I thought it was picture data.
No, this data is using Doppler data.
Don't they have to look at the
Also-
deformation of the crust?
No, they're doing tidal deformation.
They're also
They're
also
doing love
using-
number measurements.
Or are you just saying that because you like me?
I think. Well, maybe. Yeah.
Well,
The pictures did come
pictures
in
of the
looking.
poles
Yeah,
that
looking
saw
at
the volcanoes on the poles were
Yeah.
pictures.
But the paper that talks about the tidal deformation is using tidal deformation, which is a gravitational measurement, and uses radar. It uses tracking of the spacecraft.
Well then, okay.
By combining Juno and Galileo Doppler data from Deep Space Network and astrometric observations, we recovered the tidal dissipation parameter. Shallow global magma ocean in Io does not exist and are consistent with Io having a mostly solid mantle.
Okay, cool.
Whoa.
Thanks for that clarification.
I don't know
I'm
why.
still
but that's
happy
just
there's
bumming me
a
out.
camera.
Sorry?
Why is this bumming you out? You want to...
I want it to have a magma ocean.
Sure.
It makes more
now
sense.
it has magma seas instead.
Yeah.
Right.
It still has
Right.
molten magma, obviously, in the interior. Yeah, okay, well, I
Just really threw you off now. Sorry.
yeah, no, you did. No, that's very interesting because, and I was bringing my own sort of Saturnocentric Cassini bias to it because a lot of the studies of like what's going on there and like Mimas maybe has an ocean is based on really careful imaging of the wobble.
That's what I
of the
was thinking
shell
from the article. Yeah.
and seeing that the craters are wobbling. The shell basically is wobbling faster or slower
Yeah.
based on there's like water lube underneath that outer shell.
Water lube.
Water is a great lubricant.
It is.
Great.
Not that good.
So okay, cool.
Yeah.
So no, and do we know? Yeah, we don't.
No,
really know
we don't
why.
know, and
All
like
we know
it's
is it doesn't have it.
yeah, and just to like a button on the confusing aspect of it is there are hotspots on Earth, like underneath Hawaii and Iceland, and we don't really know why they're
Why
there.
is there hotspot?
Yeah,
for their
so we don't
particular-
understand
sure.
hotspots on Earth
at all.
at all, and so now looking at Io, it's just whoa. There are more questions, which is always exciting.
Okay, let's shift gears to stellar astrophysics.
100 terawatts of data or of temperature. Sorry, I just
terawatts.
yeah. The power
What?
of the total power to put into tidal heating in Io was 100 terawatts.
100 terawatts of power.
Sorry. That just okay, sorry.
10 to the 14 watts. That's a lot of zeros,
lot of
but a
power.
watt is pretty pathetic. So,
Tell it you said that.
Rude.
so one of the things we study in sort of basic stellar astronomy is different kinds of stars, and some stars are classified by like the first star that was discovered this way. So like there are some variable stars that are just named after the first star that was seen to be that particular kind of variable. So like, what's the famous variable star for measuring distances?
Cepheids.
Cepheid variables. And
He was looking at you, Jim, but I answered instead.
yeah. And so
Sorry, I can only see you, Eddie.
I know.
So.
it's named after one particular star. There's another star that's like the originator of a category called T Tauri stars, named after the star T Tauri in the constellation Taurus. It's a variable star. It's a young star. So it hasn't even started. It's like, it's brand new.
It's a baby.
It's a baby.
Young star.
It's in it's
Like
coming
Selena
out of the.
Gomez.
I don't think she's that young anymore.
Shoot. Who's the
Dating
young
Olivia
one now?
Rodrigo.
I don't
Who's
know.
the young one now? There's always a new young one coming along. Yeah.
I don't know.
There's a lot of young ones.
Who did you say, Jim?
Olivia Rodrigo.
Olivia Rodrigo.
Oh yeah, she just got her
She's
driver's
young.
license.
Oh my God.
Yeah.
But she
I
was
don't
know,
old.
that's
not-
She got
that's
it
like
old
21
though,
now.
maybe.
But
Yeah.
Yeah.
Well, T
Anyway.
Tauri, it may be even younger than 21.
Wow.
Years?
It's like stellar age.
Stellar relative to its ultimate
Adjusted.
age, right? It's
Like dog
it's toddler.
years?
Not like physical years.
It's toddler, I think.
Okay.
So if we imagine
So
that
the
when the
top,
star starts burning, has nuclear fusion at its core, then it's like walking around.
Okay.
So it's kind of in that transition.
Got it.
And interestingly, I hope for our listeners,
I'll be the judge.
it's stars form in a big cloud of gas and dust, blah blah blah.
Boring.
Gonna
And
sample that.
The gas and dust obscures your view, can obscure your view of the star. It settles into a disk, and so unless you're looking right edge on, you can see the star. So we can see T Tauri. It was discovered 100 and some years ago. It's highly variable because stuff is falling in. The star is still like it's a protostar. It's collapsing.
yeah, I don't even like to call it a star because
Right, it's a
not-
protostar. It's a
'cause it's not
protostar.
doing nuclear fusion yet. Right?
It's not yet doing
Oh, it's
nuclear
not?
fusion.
Right.
Right. It's still
No,
crawling.
it's still getting its energy from
Gravitational.
collapse.
Yeah. Things still
Fetus.
falling in.
Star
Right.
fetus.
Star fetus.
Okay,
Eh.
if you want.
Oh, I feel like
Infant. It's an infant.
Infant? Okay.
Yeah, it's not on the main sequence. Anyway, 100 years ago it's discovered, lots of variability that's related to the fact that it's still forming. Then 30 or 40 years ago, they discovered, there's 2 more stars there.
Oh, no.
Yeah.
Oh, yay.
So the one we know is T Tauri, now called T Tauri North. Then it turns out there's a T Tauri South that's a pair that are orbiting each other every 30 or 40 years, something
is
like
interesting.
that. Thank you.
Mm-hmm.
They put
The
one of them in
south
blue clothes,
pair-
one of them in red clothes. So they could tell them apart.
Yeah.
The South pair has a disk that's kind of lined up with us, or
Okay.
it's a more optically thick disk, so we can't actually see the South pair. That's why they were discovered so late in the visible. We can
Okay.
only see it in longer wavelength
okay.
light that can get through all that gas and dust. And the things are orbiting each other, right? These 3 stars. And we're now getting to the point, it appears, that the disk around the South pair is going to block our view of T Tauri, the original T Tauri North Star.
It'll be more variable.
So the paper, it may just go away.
For how long?
Is that something you do? I don't know. Is that what Olivia Rodrigo would do?
I don't
Touch her
know.
nose?
I don't think so.
Potentially
goes.
for centuries, right?
That's so long.
The orbit period of the 2 South stars together with the North Star isn't well known, but it's long. It's at least centuries. It might be tens of thousands
What's
of
the
years
separation?
even. I don't have that number off my fingertips, and so we've seen some big dimming of T Tauri North. Also, the variability seems to have gone way down for that star, and it may be the beginning of what the author of this paper, somewhat coincidentally, is named Tracy Beck.
That's so close.
So close.
So close, but
That's
not
her alter ego.
but not her.
That's her T Tauri star.
The
observing
beginning
alter
of the predicted great dimming of T Tauri may have begun.
Oh,
So the
no.
star may
To me,
not.
that seems a little bit, I don't know, to call it the great dimming
The great dimming.
for a
catchy.
thing that's just, I don't know.
You got to get the headlines, Jim.
Yeah.
I guess that's true.
It's
I
got
guess
to
that's
got to keep
Yeah.
up its
Gotta
social
zing.
media followers.
This is a paper under review, so
so they might make them change the title.
maybe they will object to the great
true.
dimming.
The kind of
Why don't
mediocre dimming of T Tauri.
I think
I mean, it's a pretty big dimming if you're not going to be able to see it.
yeah.
It's a big dimming, but I guess it's the
Not
impact
great.
and what we learn about it is not that great. But the
magnitude is great,
The
but the-
actual magnitude of
yeah.
the dimming is big.
Yeah.
Yeah, no, it's not great because it's like wonderful. It's great because it's big. Right.
That's
It's
what I was
there was
thinking.
such a great
It's not
dimming.
great expectations.
Right. It's If the star
Anyway.
goes from like you can see it to
This
no
is
you
the
can't.
I don't know.
That's a great dimming.
Lexicology podcast.
Yeah. All right. So we have a couple other things to talk about, but I'd like to hear we have
But we're out
special
of time.
we have special top Quark trivia first.
So, as you know, I've moved to Vermont.
Wait a minute. What?
What?
When?
Yeah, recently. And
Oh.
when I went to school earlier this week, I got
And
a
you're
visit-
still
You're
going to
back
school?
now?
still going to school. It
So many
was
revelations.
It was -4 degrees.
Brr.
And
Fahrenheit. we
obviously,
need
to
to
some of our
clarify.
listeners, that's very, very cold, and to others, it's just whatever.
I just want to clarify 4 below Celsius for our
Nope.
international listeners.
4 below.
I'm sorry, 4 below
Fahrenheit.
Fahrenheit.
4 below
below
so
zero.
yeah, I don't know how many below Celsius that is. It's still below 0 Celsius.
Further below. Yeah.
Much further below, yeah. And that got me thinking about really cold temperatures. I think we may have had a trivia before about cold temperatures, but here's your question.
Okay.
I can't
Or
wait.
series of questions.
Bring it.
You have a couple questions. 3 we'll start with.
Oh my god,
4
I can't. I
questions.
literally can't wait.
It's got to be 4. It's got to be 4. First, what is the lowest temperature ever recorded in Florida, where I left, where you guys are?
Uh-huh.
What's the lowest recorded temperature on Earth, on the surface? What's the lowest recorded temperature artificially produced in a lab?
Oh.
I think I might know that.
And then what's the only state in the United States that's never recorded a temperature below 0 Fahrenheit?
Okay.
Oh, that one sounds like a trick question.
Maybe.
It feels like a trick question. And for the third one, can I just round it to the nearest integer? Because
Yes.
then I've got it.
Oh, wait, no, you can't. The third one.
Okay. All right. Well, we'll come back to that. There was another sort of circumstellar disk related story
Mm-hmm.
that thought we could talk about has to do with what are called exocomets.
Those are comets outside of our solar system.
What?
Right. Orbiting other stars.
Mm-hmm.
And where are most of the comets in our solar system?
Out.
Out in the Kuiper Belt and Oort
Yeah,
Cloud.
yeah.
They're pretty far away.
Yeah.
Mm-hmm.
Aren't there way more in the Oort cloud than the Kuiper belt?
Do you know where
Yeah.
comets are?
Yeah.
Places it's very cold. So good segue,
Oh.
Jim.
Right.
Yeah.
Nice job.
Yeah, there are probably more in the Oort cloud. I shouldn't say probably because I think
Yeah,
we know.
we just can't
There
count
are
them.
more. Yeah, we just
We
haven't
haven't-
been able to like
we don't see them directly.
because they're
Right.
so cold and so far away. And
They're quite
small.
small and dark. So the comets, I don't know. I refer to them as like the leftover bits of IKEA furniture.
Yeah,
You know, when you're
in a nice way. We
In a ni-
mean
in a
that in a
nice way.
complimentary way.
yeah. So you put your furniture together. There's always some parts left over.
Yep.
When you put planets together,
There's
same
always
thing.
bits left over.
There's bits left over. We call some of them comets.
But these are like pre-assembly bits too.
These kind of never got
They're like-
taken out of the bag.
Yeah.
They're still in the little
They're still
plastic
in their
bag.
bags.
Right.
Yeah.
So, and in the Kuiper Belt's quite far. Audrey's obviously never gotten anything from IKEA. But
No.
in any event,
Not anything new.
in the Kuiper Belt's out beyond the orbit of Neptune, you have a lot of objects that formed when the planets were forming,
Mm-hmm.
and they can bump into each other. And when they bump into each other, they can knock stuff off. And that small stuff then creates a lot more surface area, which is heated up by the star that they're orbiting, and it glows, and then we can see that. And I just love these pictures that we've been getting for the last, I don't know, decade or so.
I know. Alma pictures.
Yeah.
Yes, these are pictures from the Atacama Large Millimeter Array and I think a different observatory also. But they're pictures that are in millimeter-ish wavelengths, like centimeter to millimeter wavelengths.
So pretty long,
Yeah,
very long wavelength.
yeah. And they give us these really cool images of disks around stars, so protoplanetary disks. And this new survey says a structure of 74 exocomet belts orbiting nearby stars.
Some of them really do not look like belts.
I mean,
Some of them look like blobs.
that's because probably
Well,
that's
you're
because
looking at them
what
edge on,
angle
probably.
you're imaging them.
Yeah.
But they're not like
Oh, some of them look
They're
like
not like-
circles,
yeah,
Yeah.
exactly. They look like amorphous
spherical blobs.
blobby blobs.
Yeah.
But
I
some
mean-
of them, some of them look, yeah.
Perhaps
Maybe it's like a
unresolved.
silk belt that's piled up on the floor.
Yeah.
I
Yeah.
don't know how to do the dynamics of that.
It's maybe like a donut, and you pull out so far enough and then make it
Ooh, we
blurry. You
should get
can't see the
donuts tonight.
whole.
And then you eat part of it.
It's like salty donuts where it's
Yeah.
got stuff on top.
Oh,
and like,
yum.
But some of them are actually quite amazingly high resolved.
yes.
And so they've sort of mapped 74 of these things,
Mhm.
and these are they can sort of infer model what the belt's physical dimensions are like, and even what the collision velocities between the exocomets that are making up these belts would be like. So it's really remarkable. We're sort of literally taking pictures of a region of planetary systems around other
Yeah, it'd be
stars.
super cool if somebody could be doing this for us, and so we would know the structure of the Oort
Oh,
cloud
yeah, that would be
better.
great.
Somebody should go to
Or-
another star
But
and
also,
take
so
a
like-
picture of
so
our
like-
solar system
So,
and
like
send it to
our
us.
Oort cloud, we hypothesize to be spherical, right? Because it's far enough out that it's
Yeah.
probably still spherical. So these are like more Kuiper belty. I think
these are
both in
belty.
distance and shape.
Are there
Are these younger systems? I mean, like, it seems like the density of comets in our solar system would be so low that those collisions would be so rare.
That's
that,
true. Yes, and they are
these
younger.
much younger systems?
Yes. Yeah.
Yeah, so a lot of times these images from ALMA and stuff are of protoplanetary disks, so they're like still forming forming planetary systems. I think these might be slightly older than some of the other ones, just because it is looking at the sort of stuff that's still out in the really cold regions, but it's
okay. So, and these are definitely exocomet belts and not like asteroid belts because they're so far away that they have to be cold. And so we are
Well, they're
thinking that they're
cold.
icy.
Yeah.
Yeah.
I mean-
because of the temperature, not because of
No spectral information. So, right, there's no
Yeah, that was my
compositional measurement to
Yeah.
say that this is made of ice instead of rock.
They sometimes get those with complementary measurements, but this data
Right.
set
Yeah.
doesn't talk about those. Yeah.
Right. So
Unresolved photometry.
the belts are mostly broad rather than narrow. They've got a aspect ratio, orbital inclinations of like 1 to 20 degrees. So relatively equatorial, if you want to think of it that way. Collision velocities, then, if you back out from that, are relative velocities up to like a kilometer per second in that that distance from a star, which is the Earth is orbiting the sun at 33 kilometers per second. So the further out you go, the slower it goes. So, it's just an interesting evolution. I have a fun small world anecdote about this paper.
Okay.
The one of the authors on the paper is Meredith McGregor,
okay.
who was an assistant professor at perhaps Johns Hopkins, used to be at University of Colorado, and she grew up in Boulder, Colorado, and I distinctly remember getting passed by her in a 5-kilometer race, 100 meters before the finish line.
Really?
When she was like 11, and I was a strapping, young, healthy, athletic, prime of life man cruising along, and I'm like, I'm having a really good, I'm setting a really good mark in this race. I'd already passed my student, I was feeling pretty pleased with myself. Then Meredith McGregor, 11, goes trotting by me like nothing. Yeah.
I hope you see her at a meeting sometime and tell her that story.
Yeah, I'm pretty sure she does not remember it.
Probably not. No.
So it's a small world. Yeah. Oh, one other thing I want to say, Addie.
Yes,
about
Josh.
the Oort cloud.
Okay.
It's spherical not because it's older, because those comets didn't form there.
They're
Oh no, they got
younger.
ejected.
They got emplaced there,
Oh.
and the scattering
Yeah.
put them in all random
scattered
orbits. Yeah.
Oh, okay.
Jim, are we answering your question, or did you have a Hubble tension update for us?
No, I have no Hubble tension updates for you. You can answer my question.
Okay.
Oh,
We,
no, I'm
next
so
week
nervous.
we'll have a sweet Hubble tension update, but we're not there.
All
Okay.
right.
If you'll
Lay
have
it on us.
you'll have it all figured out by next week.
I will, and probably by the week after that, the Nobel Prize in Physics, people.
Dang, I
I don't
that's
think
the
they
season,
announce it until
so,
the fall
yeah.
or something.
Oh,
Yeah.
crap!
That's the
All right.
only issue with that
Right.
statement.
Yeah.
Otherwise, you got it.
Mm-hmm.
All right. Remind us the first question.
All
Lowest
right.
temperature
so
in
here
Florida.
here are your questions. First question is, well, we'll go in reverse order. First, what is the only state in the United States that has never recorded a temperature below 0 Fahrenheit?
The only state
Of the 50,
anywhere in the United States.
Boy,
I
can't think of any.
I mean,
I feel like,
That's like-
Louisiana, maybe. That's the only one, because you got to think about topography.
Exactly.
right.
Even though there's some,
The
But
mind
you might say
immediately
like
goes
Hawaii,
to Hawaii.
but there's
Yeah,
mountains
yeah.
and it snows, and I've been there when it snows.
and
and
it's
it's
so
cold.
cold, even in the summer.
Yeah, those telescopes are
topography,
high
man.
up. They're,
But like,
Yeah.
yeah, Louisiana, southern state, very little topography.
yeah,
I
I
don't
like
know.
Louisiana.
Okay.
I'll say Mississippi
As a
just
state
to
or as an
choose
answer?
something else
Yeah,
as an answer.
Louisiana.
sure.
all right, Louisiana, Mississippi. The actual answer is Hawaii.
No, it's
Aw,
not.
No, it isn't.
Yes, it is.
That's
man.
wrong.
They've definitely recorded 0 temperatures on
They
the
have
mountains.
not. It's 12 degrees Fahrenheit is the lowest ever recorded on the top of Mauna Kea
Kea.
or whatever, Mauna Loa.
Huh. Well, you faked us
That-
out.
I
You
faked you
us out. Faked
It
because
us out.
I would have thought along the exact same lines as you. I was like
Wow.
Hawaii, but there's no way it's Hawaii because you always see snow at the top of it. But it never gets really really cold there.
Just cold.
Okay.
All right, what's the lowest temperature ever recorded in Florida?
I have zero confidence now.
Well, we know it's below 0 Fahrenheit.
Below 0. I'll tell you, it's a dumb question. -2 in
Okay.
Tallahassee.
I was
That
gonna
is a
guess
dumb question.
that's what I was going to
yeah,
say.
I'm
I'm
very
like,
different
question.
numbers. So
I'm saying
Given
that's
the question I already asked, it
That's
was a dumb
really
question.
cold.
Okay,
for Florida,
that's pretty cold. That was way back when, a really cold snap. What is the lowest temperature ever recorded, like climatological temperature, on the surface of the Earth?
that's a tougher one.
oh, wait, not
Do you want?
Wait,
can we give
the
it? Can we
lowest-
choose our units?
natural.
Yes. Well,
Temperature.
yes. I
Yeah.
want it in Fahrenheit. But Kelvin, I'll take as well.
What? Those are the only two I don't want to use.
You will not use centigrade or Celsius in my house.
I'm not in your
Wow.
house first, but
Yeah.
just for that, I am going to use it.
Minus.
minus 100. That's so cold. Minus 100. I don't know.
Audrey says minus 100 Fahrenheit.
Yeah.
Fahrenheit?
I'm gonna go minus 72 Fahrenheit.
Yikes.
Just pick a
I'm going to
number.
go minus 60 Celsius.
I think Audrey has it. It's minus 129 Fahrenheit.
Yes!
Wow.
Wow.
Where?
That's significantly cold. What is that?
In Vostok, Antarctica.
What is that?
Antarctica.
What is that in Kelvin?
That's 184 Kelvin.
That's so
That's cold.
cold.
That's very, very, very cold.
Now you think that's cold. Now that it's in Kelvin. Does your phone
Minus
tell you
one-
temperatures in Kelvin?
Minus 120 is like, meh, I can handle
That's
that.
129. The lowest temperature in the continental United States is minus 70 in Montana.
Oh, so that's
and,
what the answer. That's what I was
yeah.
answering. I just
That's
got
what you were
confused.
answering.
Yeah.
And finally, to close it all off, what's the lowest temperature ever produced in a laboratory? Of course, we're interested in physics and studying how things behave at low temperatures.
Yes.
I'm going to go.
I'm
We do
going to
a
go
very
with
good job of
0.
getting those temperatures low.
Point
Here, I will
four.
accept answers only in Kelvin. Of course.
0.4.
10,
Kelvin.
4 Kelvin,
10 millikelvin.
10
See,
millikelvin.
so you're saying 0.02, right?
Sure.
I'm saying 10 to the minus 6 Kelvin.
It's 10 to the minus 10 Kelvin. 100
No.
picokelvin.
What?
Insane.
0.
Who did it?
I said 0.
I know.
Crazy.
Yeah.
All right.
Who did
Tell
it?
us where.
I don't know who did that. I don't know.
Oh, Jim.
Why do we
But
go
they
to
do
those
it.
super low
it's
temperatures, Jim?
what's really interesting. I mean, I won't go through the whole thing, but it's really interesting about how they do it. Because like usually when you make things cold, you just like put them in contact with something colder.
Can't
But
do
obviously you can't do that when you're trying to get the coldest things essentially in the universe, and so you have to do all these funky things to do it. They use weird nuclear. Anyway, I don't even understand it.
Well, but the point of it is what? Why are they doing these crazy things?
They're doing these things to see, because when you cool things down to very low temperatures, they exhibit weird things. Like you make Bose-Einstein condensates and fun things like that. When
I did
electrons
in
all
undergrad.
blob together.
I worked on an adiabatic refrigerator, and we got down to 40 millikelvin.
Wow.
Yeah.
Uh-huh.
Nice.
That's tremendous. Yeah, it's that kind of that thing. Those
Thanks.
adiabatic refrigerators, but they use funky systems,
should
funky
build one of those
nuclear
and do
systems
some-
to do it.
Yeah.
it's
I mean,
crazy.
now it's also for quantum computing. Low
Yeah.
temperatures are required, not 10 to the minus 10.
That
but
it was
getting
for
down
it was for
for
quantum
computing.
thing.
So
yeah.
you need to get
That's
things
awesome,
down
yeah.
to reduce. You need to keep your qubit stable. Mm-hmm. And so
qubits are
very,
never
very,
stable?
very, very low temperature. Right. Well, while it may have felt like a final exam in a subject you've never taken, it was just another episode of Walkabout the Galaxy.
Be sure to follow us on Instagram and YouTube. You can contact us at wtg@ucf.edu.
Our theme music was composed by Richard Drusik. Production assistance is provided by Logan Basinger.
Thanks to our listeners in Kentucky. I'm Jim Cooney.
I'm Audrey Martin.
I'm Josh Caldwell.
And I'm Addie Dove. We're the Astrocorks, signing off until the next episode of Walkabout the Galaxy.
Woohoo!
Bit.